We will very briefly touch upon the hardware upheaval caused by the many core processors and the software shortfall in terms of exploiting the parallelism and performance of many core processors. We introduce a new computing model that exploits the parallelism and performance by overlaying a signaling control architecture on top of the von Neumann serial computing model. We show that this provides the architectural resiliency of cellular organisms and improves availability, reliability, performance, and security. We apply this model to a web server platform with Linux, Apache, MySQL, and PHP components to demonstrate self-repair, auto-scaling, live migration, and transaction security. We conclude by making some observations on future research. I recommend von Neumann's Hickson lectures for many insights on which our results are based upon. The new computing model is discussed in my book, Designing a New Class of Distributed Systems, published by Springer. You can ask, what's the big deal? We can do it in cloud computing today. The trick is to do it without using hypervisors and drastically reducing the management complexity. We set out 3 design goals. Number 1, to improve the total cost of ownership by orders of magnitude without counting the power, space, and cooling improvements offered by many core servers. Number 2, make it easy to migrate. And number 3, drastically reduce the professional services component in IT. As is being emphasized in this conference, the many core server is indeed causing an upheaval with its parallelism and performance. The 32 core and the 48 core microprocessor chips are causing a discontinuity in the IT industry. The sea change is not my word. If you are a bellhead like I am, it is easy to imagine an architectural transformation of current data centers from their current role of resource management to services switching. When you have hundreds of or even thousands of cores inside a server with high bandwidth connectivity, much of the current generation server, networking, and storage infrastructure with their server-centric and low bandwidth origins become obsolete. Who needs fiber channel switching? Does TCP/IP communications make sense inside the enclosure? Do the current operating systems with their lock-based implementations scale inside the enclosure? So we can envision a new architecture where the big servers operate as clouds and the switching architecture is completely optical. If server is the cloud, then what is the obstacle? Current distributed computing models have evolved from their server-centric and bandwidth-limited network architectures. The von Neumann serial computing model is essentially a node-centric computing model and is not ideal for a network-based computing. It mixes both resource management and service execution in a serial fashion, as shown here. And a network of nodes essentially have evolved into a web of complex management systems that manage end-to-end distributed transactions. There are 2 problems with this approach. Number 1, end-to-end transaction response time is no longer controlled by the node operating system. The transaction resiliency requires network-wide resolution of contention for resources that impact the transaction based on workload fluctuations, business priorities, and latency constraints. Current management strategies provide no easy visibility and control of end-to-end transaction management, and therefore lack the telecom grade trust. Using the new computing model that exploits the parallelism and performance of many core servers, we implement service-centric visibility and control, which allows service virtualization without the need for current hypervisors. We provide service virtualization at the process level in Linux and at the core using a new native operating system called Parallax. I will present process virtualization and its use in this talk. The service management provides visibility and control of end-to-end transaction across multiple processes, whether they are in the same physical container or not. The resulting decoupling of service management from underlying hardware management allows reliable services to be implemented on not so reliable hardware, thus bringing the architectural resiliency of cellular organisms that von Neumann was seeking in his Hickson lectures. Even as many core processors are under development, there are already many core servers available today for commercial deployment that are using multi-core, dual and quad-core processors. However, current operating systems do not have visibility to all the cores, and therefore multiple OS images are deployed in the same container. These images communicate with each other using socket-based TCP/IP. End-to-end transaction management is provided through the orchestration of multiple management systems. We start with a self-managed computing element, which is a managed Turing node with fault configuration, accounting, performance, and security management. We add context-sensitive computing with the dynamic policy management, which supports, for example, communications via shared memory or high-speed or low-latency bus or a socket. And we add a parallel signaling network overlay, which allows us to manage end-to-end transactions across computing elements in real time. This picture shows the many-core server network and the new computing model deployment. Notice that there are 3 levels of networks with different bandwidths, and also notice the recursive nature of network composition. The non-von Neumann computing exploits parallelism and recursive composition of FCAPS managed nodes. The key innovation is the introduction of signaling-enabled managed Turing machine and the dynamic context-sensitive communication and policy implementation. We transform the Turing machine implementing von Neumann computing into a distributed intelligent managed element, which implements the non-von Neumann managed Turing machine. The control network is an overlay over the current von Neumann serial computing network. Each Linux process is then controlled by the FCAPS management, and essentially we convert every Linux process into a managed computing element that provides fault configuration, accounting, performance, and security management. The control network allows to set up the various parameters that are required for executing the process, and it can start by loading and executing the process executable. The control network also allows you to stop the computing machine at any time you desire based on policies. and you can also restart, for example. So this picture shows a simple service being controlled, loaded, and executed. I will describe now how we have used process virtualization to create a network of DIMEs implementing Linux, Apache, MySQL, and PHP based web service with auto scaling, self repair, and end-to-end transaction FCAPS management without using Hypervisor or other resource virtualization and management frameworks. Each component is encapsulated as a DIME, and the application or service running in the mice is controlled by the FCAPS manager. The fault and performance information from each DIME is collected through the signaling channel and is utilized by the end-to-end DIME network management infrastructure implemented here in the administration panel. The policies are implemented by the DIME network configuration manager, including the supervisor, fault manager, performance manager, accounting manager, and the security manager functions designed to execute policy implementation workflows. The DNS provides the primary and the secondary list of the Apaches encapsulated in different DIMEs with different addresses. When the primary DIME fails, the secondary is replaced, and also automatically the DNS is updated to show the new configuration. The performance information is monitored from the Apache web server and is used to scale additional Apache servers and update the appropriate DNS entries so that the load balancing is accomplished as you scale up or down. This picture shows the performance characteristic, which is the response time, as a function of the request. As you can see, as the performance degrades, we can add additional DIMEs and control the response time. This shows another configuration where 3 DIMEs are used as Apache servers to improve the performance as the number of requests increase. This picture shows that we can dramatically increase the performance by improving the response time as a function of the number of requests by adding 2 DIMEs instead of 1 DIME. It is interesting to look back at what von Neumann said in his Hickson Symposium in 1948. It's very likely that on the basis of philosophy that every error has to be caught, explained, and corrected, a system of the complexity of the living organism would not run even for a millisecond. We believe that the DIME computing model, by introducing the managed Turing machines, brings the cellular architectural resiliency to computing infrastructure. I have 2 video links here which show the parallax operating system and also DIMEs in Linux approach. Thank you. Other questions? I have a few minutes, or you can always email me at rao@kavaobjects.com. Thank you. This table shows the comparison between conventional computing, cloud computing, and dime computing. In the case of conventional computing, the physical server is the base computing unit, whereas in a virtual cloud computing environment, virtual server becomes a base computing element. In dime computing, in the process based virtualization in Linux, a process itself is a base computing unit, and in parallax, a core becomes a computing element. Now, we have listed here various characteristics and the differences between the three computing models. As you can see in the last row, the management latency is different in different computing models. The dime computing model essentially provides real-time management where the service transaction time and the service management latency are approximately equal. This picture shows the evolution of pots, pans, and distributed computing. Obviously, the AT&T Bell Labs contribution to the first cloud, which was the voice cloud, was to connect billions of users using plain old telephone service pots. With the introduction of the internet, billions of devices were connected and provided a platform for pretty amazing new services, the PANs. Now we have a new opportunity with the distributed clouds where the server is a cloud and a federation of clouds will provide connecting services to trillions of managed and distributed services. Thank you.